But my hope will never die.
What's up, guys? Welcome back to another Algebra 2 instruction lesson here with Mr. Gaines as we look to wrap up our work on logarithmic functions. Today, we are going to get into some applications of logarithmic functions. So let's go ahead and go right into examples. In problem number 8, we have the magnitude intensity of an earthquake that can be measured using the equation m of I that is equal to log I over log I sub 0, where I is the measured intensity and I sub 0 is a minimum or reference intensity. So the Great San Francisco earthquake of 1906, which is one of the deadliest earthquakes ever recorded in the United States, had an estimated magnitude of 7.7. The 2004 Indian Ocean earthquake had a magnitude of approximately 9.1, which triggered a series of deadly tsunamis. What we want to figure out is how much more intense was the 2004 quake. So intensity is the measure I in this function. So what we need to do is basically find the intensity of the San Francisco quake and compare that to the intensity of the Indian Ocean quake. So let's first start with the San Fran quake. So we're going to use this equation for magnitude, which is equal to log base 10, because it's the common log base 10 of intensity over a reference intensity. So for the San Francisco quake, we know that the magnitude was 7.7. So I can substitute this into the equation. So 7.7 is equal to log base 10 of the intensity I over I sub 0. And I'm going to actually make this I sub s, because this is going to be the intensity of the San Francisco quake. I sub s over I sub 0. Now, we don't know what I sub s or I sub 0 is in this case. But what we can do is we can rewrite this from a logarithmic equation into an exponential equation. We can do this to try to isolate the intensity of San Francisco quake, the I sub s. So in rewriting this function, remember this is of base 10. So the common log has base 10. So rewriting this function would give me 10 to the 7.7 power, the output of the logarithm because the input of the exponential function, equal to I sub s over I sub 0. Now, if I want the intensity of the San Francisco quake by itself, I'm going to get I sub s, which is the intensity of San Francisco, isolated. So the intensity of the San Francisco quake would be 10 to the 7.7 power times I sub 0. Now I want to do the same thing, excuse me, for the Indian Ocean quake. So if you kind of understand how this works, go ahead and pause the video at this point to see if you can find what the intensity of the Indian Ocean quake was as an equation. If you had a chance to get an equation, go ahead and check your work with what we're about to do. If you could not figure it out, go ahead and follow along. So the magnitude of the Indian Ocean quake was 9.1. So I'm going to substitute in 9.1 for m sub I. And I still have the equation, the common log or log base 10 of, let's say in this case, I sub I, that's not ideal, but I sub I for Indian Ocean intensity over I sub 0 for initial intensity. And in this case, I'm going to go ahead again and rewrite the function. So the base would be 10. The exponent would be 9.1, the output becoming the input of the exponential function. So 10 to the 9.1 power. Get this to right here. There we go. 10 to the 9.1 power would be equal to the input of the logarithm, I sub I over I sub 0. Now, I sub I is the intensity of the Indian Ocean quake, so we want to get that by itself. We want to isolate this. So this would be 10 to the 9.1 power times I sub 0. So if I want to compare their intensities, I could do a little bit of a ratio or a division here. I could take I sub I the Indian Ocean intensity, and divide by I sub S, the San Francisco intensity. What this would give me would be a value that would tell me how many more times the Indian Ocean quake was in terms of intensity compared to the San Francisco quake. So in this case, the I sub zeros are going to cancel out. So the intensity comparison is actually going to be 10 to the 9.1 power divided by 10 to the 7.7 power. And here we have that the Indian Ocean quake was approximately 25.12 times the intensity of the San Fran quake. So if we were to be feeling the earthquake at the epicenter of the San Fran quake in comparison to the Indian Ocean quake, the Indian Ocean quake would feel approximately 25.12 times more intense than the San Fran quake, which is the most deadly in the US. And so we have a drastic difference in this intensity. Now, again, what we did here, the focus here was rewriting the logarithmic equation in terms of I to be able to compare their intensities. Now, let's take a look at a different example. Problem number 9 says the altitude or height above sea level for any position on Earth can be determined by the barometric pressure using the formula H equal to 30 times T plus 8,000 times the natural log of P sub 0 over P, where H is the altitude in meters, that's going to be important, for temperature T in degrees Celsius, also important. P is the barometric pressure in centimeters of mercury, and P sub 0 is the barometric pressure at sea level, which is 76 centimeters of mercury. Hikers at the summit of Mount Shasta in North California take a pressure reading of 45.1 centimeters of mercury at a temperature of 9 degrees Celsius. How high is Mount Shasta? So what we can do here is we can find the height above sea level just by knowing the barometric pressure. And so you can take a device to measure barometric pressure and determine height. And this is pretty common. Now it's advanced, a little more advanced, but this is a pretty common method to find this height. So we want to find out how high is Mount Shasta. We want to eventually solve for H. So what we know here is that the temperature, wherever we're at currently, is 9 degrees Celsius, where they are on Mount Shasta. So what we would have is 30 times 9 plus 8,000 times the natural log of P sub 0. P sub 0 is the barometric pressure at sea level, which is 76 centimeters of mercury, over P, and P is the barometric pressure of the current location, which in this case is 45.1 centimeters of mercury. So we can allow the calculator at this point to do the work for us. So we can substitute in the values, the measurements that were recorded at this location on Mount Shasta, and substitute them into the formula that we were given. And then let the calculator evaluate that formula to find that the height of Mount Shasta, this location on Mount Shasta, is approximately 4,315.71 meters above sea level. So here we have just an evaluation of an equation. We have to read for context and to identify which numbers are substituted into which locations for variables, but then it's just an evaluation and we can allow the calculator to do that work. Now, if maybe we were trying to solve for the temperature and we knew the height, then we would have a variable t here, and we would have to rewrite our equation to solve for t. In this case, not something that we're going to have to worry about for this problem. Let's take a look at one more example, And in this example, we have multiple parts to this problem. In problem 10, it says market research has shown that the sale of Music Master, a new system for downloading and playing music, can be approximated by the equation S of D equals 2500 plus 250 natural log of D, where S of D is the number of sales after D, $1,000 spent on advertising. Question A says, what sales volume is expected if the advertising budget is $40,000? So we can, in this point, we can solve this problem a number of different ways. What I'm going to go ahead and do, because I have multiple questions relating to the same function, is I'm going to go ahead and sketch a graph. And then I'm going to use the graph to solve these problems. Now, if you would prefer to solve them algebraically, that's an option that you would have. As we solve this graphically, though, we want to make sure that we label the axes of our graph. So this is the function S of D. So S of D is the number of sales. So I want to label the y-axis as number of sales, or we'll just label it as sales. After D, $1,000 spent on advertising. So we'll make this advertising budget. And this is in thousands of dollars. So we're not exactly sure how far that we want to take our graph out here. But let's go ahead and let's put this graph into the graphing calculator, or this function. So 2,500 plus 250 times the natural log of, we're going to use X in this case to represent the dollars spent on advertising. And I'm going to go to my window. I'm going to set the X minimum to 0 because we know we're not going to be less than $0 spent. In problem C, it starts talking about having $83,000 spent on advertising. So I'm going to go at least past 83,000 to 85,000 here. And then I'm going to go ahead and hit zoom and hit 0, zoom fit, to adjust my window on my graphing calculator. And so we see a graph here that represents our equation. And I'm going to go ahead and bring the window. I'm going to make a small adjustment to the window. I'm going to bring the y minimum down to the the x-axis, y equals 0, because this is going to better represent the picture that I've kind of sketched out here. And so this is our graph. So when sketching in this graph, I realized there is no horizontal shift to the graph. So this is going to have a vertical asymptote of 0. So it's I'm going to sketch this graph to look something like what we have here. And it looks like it's really rapidly approaching or moving to the right. And it's got a vertical asymptote of x equals 0. So I'm going to kind of sketch that into the curve. And now we can use this curve to answer some questions. So question number A, or letter A, says what sales volume is expected if the advertising budget is $40,000? Well, remember, advertising budget is the X value, and it is in thousands, so I'm going to look for the value on my calculator, 40. So I can either do that on the table or hit second, trace, select value, and then I can type in a value for X. X equals 40. So this point, it's kind of covered up by the letters there, but we can see the decimal approximation. I'm going to label this point on my graph. This point is 3,422 point. Let's go ahead and run it out to 2 decimals, 22. So again, it says what sales volume is expected if the advertising budget is $40,000. So we're going to expect to sell approximately 3,422 downloads or sales. So you could have gotten to this algebraically by substituting into the function the same number, 40, or graphically by graphing and finding the point on the graph. In part B, it says if the company needs to sell 3,500 units to begin making a profit, how much should be spent on advertising? So we need to sell at least 3,500 units, maybe more, but at least 3,500 units. Well, the 3,500 units or 3,500 downloads would be the Y value, the S of D value. So on my calculator, I can hit y equals, and then I can type in the number 3,500. And then as I look on the graph, I'm going to see a horizontal line that intersects with the graph. So I want to find this intersection. So I'm going to hit second, trace, intersect, which is 5, and make sure my cursor is close to this intersection. Hit enter on the first curve, enter on the second curve. We don't need to guess, and it finds the intersection for me. So I'm going to go ahead and label this point. This point is 45 point, and remember the x coordinate is in thousands, so I'm going to carry this out a little bit. This would be 45,598, and then I'll go to 2, 5982, and 3,500. So it says how much should be spent on advertising. Actually, let me go a little bit further on my rounding. Let's go 35,59815, and then 3,500. So that will carry me out to the cents when I convert this to thousands. So the x coordinate is my advertising budget, again in thousands. So we would be wanting to spend greater than or equal to this amount. So greater than or equal to $45,598.15. So we could potentially work that up to 44,000 or $54,600, but we know we need to spend at least this amount, if not more. If we spend more, it's going to increase our sales. Our sales is still moving upward there, so we need to spend that number or potentially more. In problem C, it says to gain a firm hold on market share, the company is willing to continue spending on advertising up to a point where only 3 additional sales are gained for every $1,000 spent. In other words, the average rate of change is going to be 3/1. Verify that spending between $83,200 and $83,300 puts them very close to this limit. So they're giving us the X values here. And so let's go ahead and let's find these values on the graph. I'm going to go ahead and switch to the table. So hit table set here, and I'm going to go down to 83, and I'm going to make it change by 1/10. So if I look at the table, 83.2 is $83,220. So the change in the X over change in Y is what we're looking for, change in S over change in D. So my S value here would be the Y value, which is 3,605.3. And my change in D would be the X value, which is 83.2. I'm going to go on to the next point, which would be 83.3 on the X, and 3,605.6 on the Y. So if I find the change in X over the change in Y here, we can see that this would be approximately negative 0.3 over negative 0.1, which simplifies to 3/1. And so we can see that at approximately $83,200 or $83,300, they would be reaching that spending difference in relation to sales and would no longer want to continue advertising. So here we see a variety of different ways that we can apply logarithmic functions. This is the conclusion of our section here. So as we progress, we'll be looking forward towards some more practice and then soon assessment. As always, thank you guys for tuning in, and we'll see you soon.